Captain Tsubasa, do you want to learn a way to predict the outcome of a sports even before the matches have been played? Do you want to win almost every bet against your friends? All you have to do is watch this video all the way through the end and try the exercise presented it on your own. Here, we are going to talk about the Qatar Football League, Qatar Stars League, starting by showing the teams that play in this league. We can see that every team has to play each other 2 times in a double round robin, one game playing at home and the other playing away. Like we see here, we have the 12 teams that are joining the league this year, and this is the 2020-2021 tournament. Analyzing the results of the 2020-2021 tournament, we're going to get the following data shown in this project: the empiric and the binomial distribution, the maximum number of goals in 90 minutes, the Poisson distribution, showing some graphs and tables, and finally, simulating the league with a Monte Carlo, using a programming code and combining different functions to simulate the tournament results and get a similar outcome as the real one. We will get the probabilities of the teams winning, losing, or tying, and the probabilities when they play as a local team or away, the total of goals, and a table showing the average goals, goals in favor, and goals against. Like we have the number of games that we will play, the local team, the away team, the goals from the local team, the goals from the away team, and the total number of goals for each team of the league. So now let's get to the exercises.
Okay, so here we have the total of teams of the Qatar League, which is 12, the total of games, the minimum of goals in a single match, and the maximum of goals in a single match. So then, once we got the complete data referred to the Qatar Football League from 2020 to 2021, we can explain the empirical distribution, which has a frequentage approach due to the limits, which are 0 and 9, and the sum of this column is 1. Then we have the empirical frequency, which tells us in how much games there were 0, 1, 2, 3, and so on until 9 goals. How many of those goals were in a single match? Then we have the binomial distribution, which assumes that it is possible to only make 1 goal per minute. So theoretically, in one match, you can make 90 goals. And this here is a probability of having 0, 1, 2, and 3 goals, and so on until you get the maximum of 90 goals, because it is 1 per minute. Then, after making too many experiments of the binomial distribution, we realized that this converges to the Poisson distribution when the parameter n tends to infinite. What is n? N is the number of independent Bernoulli experiments realized in a period of time, which was 90 experiments in the case of the binomial distribution. So in the Poisson distribution, we're assuming that there can be an infinite numbers of goals in a single match. And below here, we have the graphs to show visually how they are distributed. So here's the empirical distribution, the Poisson distribution, and the binomial distribution. And this fourth graph is a comparison of the three, which is the empirical distribution is the greatest because of the limits, which are very low. Then the binomial distribution, it's also a little bit high because there are only 90 experiments, and the Poisson is the most precise graph because it is like infinite possible goals in a single match instead of 90 or just between 0 and 9.
So for the procedures we'll be doing afterwards, We've summarized our information in this table. First, we have the name of the teams, how many games they play locally, how many games they played as away teams, the goals they've scored locally, and the average, which is obtained by dividing the number of goals by the number of games. In this case, the number of local goals they scored divided by the number of games they played as home. The same thing occurs for goals scored as visitor or away. And well, we add them up in a total. We also have goals they've received locally with their respective average and goals they've received as away teams and the additions too. This information is important because that's where we'll be getting our simulation parameters for the next procedures, which is where we'll simulate these results.
Okay, so before we can begin to do the simulations, we first need to understand an important concept, the inverse transform method. To understand this method, we first need to understand how probability distributions normally work. So let's check. So here we have a group of probability distributions. Usually we go from the random variable support to the probability distributions. So what we basically do is that we go from value to probability, value to probability. But in the case of the inverse transform method, we do exactly the opposite. So we go from a random probability to its corresponding value at the random variable. Okay, so let's keep that in mind. We go from a random variable, from random probability to its corresponding value at the random variable. So let's keep that in mind and check how we can code this process for a Poisson distribution. So here we have the code. As I have said before, we start from the random probability. So here we have it. We also define our Gauss counter, and these two auxiliary variables that will help us to calculate the probability distribution of the Poisson variable. So, okay. So here we have a loop. Let's see what does this loop do. As we can see in this line, we are calculating the mass function of the Poisson variable. It is not difficult to see that this expression, and keeping in mind that the value of p is this one, that this expression calculates the mass function of a Poisson variable. What we do here is that we accumulate the mass function. So we update the f value by adding this mass function. And finally, we update the value of our goal counter. It is not difficult to see that our f variable increases in each iteration of the loop. So our stop condition will be once the f value is greater than our random variable, our random probability, the loop stops. This loop's outcome is the number of goals. So, as we have seen before, our code generates the number of goals that a team scores using the inverse transform method for a Poisson distribution. So since we are talking about a Poisson distribution, we need to calculate these lambda parameters. So let's take, for instance, this match between these teams. And of course, since we are talking about a match, we do know that a match implies the interaction of two teams. So we need to calculate two lambda parameters, one for the local team and one for the visitor. So let's see how we can do this. For the case of the local team, we simply multiply 0.5 times the average goals that the local team scores as a local team, plus 0.5 times the average goals that the visitor receives as a visitor. For the case of the visitor, we multiply 0.5 times the average goals the visitor teams scores as a visitor, plus 0.5 times the average goals that the local team receives as a visitor. Okay, so now we already have our lambda parameters, and now we can use our function, and let's see what we can get. So here we invoke our function. We put the lambda parameter from the local team, and we get one goal for the local team. Let's do the same as well for the visitor. We invoke our function, we put the parameter, and we get one goal as well for the visitor. So for this first simulation, our result is that the teams tie. And of course, we can do this same process for as many times we want. So we can do this several times. And of course, for each of the times we do this, we get the result. If the local team wins, if the visitor wins, or if they tie. Okay, so at this point, now we are ready to simulate a whole season. So first, what we do is that we calculate the lambda parameters for each of the matches in each of the teams. So here we have two columns. The column for the lambda parameter of the local teams and the lambda parameter for the visitors. Okay, so let's check how can we code the simulation of the season. These two functions, goal home and goal away, are just the exact same function that we have already seen. So let's just focus on our Monte Carlo subroutine. We first define the number of simulations we want to do. We define the home variable, which will help us to save the number of goals that the local team scores. The variable away will help us to save the number of goals that the visitor scores. These two variables are just auxiliary variables. And these two vectors will help us to save the lambda parameters, the value of the lambda parameters that we have already calculated in the worksheet. And these three variables are just counters. Home win counts the number of times the local team wins. Away win counts the number of times the visitor wins. And tie the number of times two teams tie. This first loop just saves in each of the vectors the parameter values for each of the cases, for the local teams and for the visitor. So here we have to loops. What we basically do here is that we simulate each of the teams 10,000 times, or just the number of times you want. So we start the loop and we will do it for each of the matches. We initialize our counters with value 0. And what we do here is that we do the end simulations of the matches of the match of the corresponding match. So here we generate the number of goals that the local team will score, and we save it in the home variable. We do the same as well with the visitor. And what we do here in this conditional is that we just count each of the results. If this happens, we add a win to the counter of the local wins. If this happens, we add a win for the counter, or to the counter of the number of times the visitor wins. And if none of this happens, we add a 1 to the tie counter. And finally, we just print these results: the proportion of times the local team wins, the proportion of times they tie, the proportion of times the visitor wins, and we also calculate the expected points that each team will have for each match. So we have 3 times the proportion of times the local team wins plus 1 times the proportion of times they tie, 3 times the proportion of times the visitor wins plus 1 times the proportion of times they tie. And that's basically how this count works. So let's see what we can get if we simulate a season. So let's just put right here 10,000, and let's just wait for the results to appear so we can see how these probabilities are changing. And let's just wait for the code to run and see what we can get. So it seems like it is done. So here we have each of the probabilities for the probability of winning for a local team, the probability of tie, and the probability of winning from the visitor, and the expected points that the local team will have, and the expected points that the visitor will have.
Well, finally, once we have already simulated all the games in the season due to 22 dates per team, we can see that having as entry the expected points per team, considering the initial probabilities of receiving goal and away and receiving goal at home, then we can consider the following results of the season simulated 10,000 times due to the large numbers law. And here we can see the authentic results of the season observed. And here in this table, we can observe the simulation results, where we can see directly that almost all the teams conserve their original positions, except in this middle table segment where there are a little bit some changes, and it can be considered normal due to the middle probabilities they have between them to receive or to score a goal. Here in the top of the table, we can observe Al Saad has the leading position with 50 points in the simulation and 60 points in the real tournament. Here we can also deduce that even when there is a variation between the points in the simulation and the real game, there is still so much difference between the first position and the second one, which means the supremacy of this team is greater than the supremacy in between the others, because its capacity or ability to score a goal and not receiving so many goals. The other way around, in the bottom of the table, we can observe the worst team is the same in the simulation than in the real tournament. Even when in the simulation it has some more points than in the authentic results, we can see that it was not enough to gain any other position, and it's also in the lowest part of the table. But finally, as a conclusion of this work, we can observe and we practice with the law of large numbers, which states that having so many simulations of one or of one single tournament in this case, we can demonstrate the 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 the, the path it will follow, tending to infinite repetitions. In this case, there were 10,000 simulations, enough to acquire these results, which were actually really similar to the real results here. And to end, we have to consider that we used an observed past season in order to do this analysis, where we could compare the results and observe which were the variations. And it's important to remember that this part was constructed by the data. In this case, we have the results of the games per season, per week, in the first, second, third match, all the way around to the 132 match. And these results from crossing each team with the other one 2 times, one away and one for local. And in this case, we also have the scores and the statistics of the maximum and minimum goals in the season, the average goals per match, and the average goals per minute. And having this data, we were able to simulate and calculate the mean of the expected points each team will do. And this is why when we cross over each team with the other one, we have these results here. And we can conclude that this kind of analysis was really similar to the real results, due to the amount of simulations we did and due to the data used from one thing that is already observed.